So thank you very much. Thank you very much for the invitation. So first of all, I would like to thank two persons who helped me in preparing this presentation. First of all, France Boileau-Cerneux, who is leading the ANAMI project, and also Guigon Camille, who is working with me on AI and data policy and strategy at CA level. So my talk is about international collaboration in high-performance computing, and I will try to highlight, I hope, some success and challenges. So the outline of my talk. So first of all, I would like to start with some discussion about technological shifts in high-performance computing. And I think there are also some points which is quite important when we talk about international collaboration is the geopolitical context, and try to figure out how can science navigate in this context, and finally how to improve international collaboration. I try to make not a cooking, but try to find the main ingredient in if we want to make an HPC cake. So first of all, I think we have to take some scientists, and of course, all we done in HPC context, but also in AI or scientific computing, let's say, in general, is to identify the applicative areas and the targets we want to solve. We have also to mix some computer scientists and tech people, some high-end technology, from semiconductors, high-speed interconnect, CPU, GPU, and so on. And of course, also some politics about national strategy, international collaboration and competition, money, and a lot of money. So I think if we mix all these ingredients, you can have at the final time with a more or less delicious HPC cake, and we can mix also this recipe with some QC and AI, and you mix the different elements and you obtain similar cooking at the end. So I think we have been eating HPC for some decades, but it seems now that HPC, classical HPC, is not as famous as it used to be. And if you take, for example, all the speakers we had during these 2 days, we talk more about AI, quantum computing, than classical HPC. So if HPC is dead, if yes, long life to what? And this is one of the questions we have to address. So if we look back into the future, back to the future, and to see about technological shift in HPC, so I will try to make HPC story in a nutshell. It's a hard exercise, but I try to do it. So if you look at the beginning 40s, between 40 and 70s, we have many big mainframes where we can achieve some, let's say, scientific computation. After that, we have the era of vector machines, essentially with small, not small, but a few main constructors, namely Cray, but also some companies from Japan, like Fujitsu and NEC. At the same time, not really at the same time, but between the 90s and after, we saw the arrival of cluster area and the first, let's say, MPP systems, where now we have only MPP systems between up to now. But if you look at some shift during this period, concerning the architecture, we saw that a large increase of use of GPUs instead of classical CPUs. And if you look at the top 500, you see that more than 90% of the total peak performance is based on GPU, and essentially NVIDIA and AMD. But also, if you look at the usage of these supercomputers, you see more and more use of AI and less classical HPC. If you look now on about the history of GPU, I say from video games to AI. Initially, GPU have been designed for video games, so to do some graphics. It has been used for HPC essentially because it offers excellent ratio gigaflop per watt, and this is a large concern concerning the HPC ecosystem. And now the GPU market is led by AI and generative AI. And if you look at this market and the use of AI and generative AI, double precision was useless. So I put on this plot the performance of NVIDIA GPU, the last version of the NVIDIA GPU from V100 to B100. And if you look at the peak performance in teraflops, depending on the precision, you see that a large increase of less precision, FP16 or FP32, and a quite flat curve about the performance of double precision. So GPU is not mainly especially designed for numerical simulations. It's designed first for accelerating graphics, now for accelerating AI workflows, inference and learning. It's not really easy to program, so at the first we use native language furnished by the providers like CUDA or OpenCL. And they are also to deal with explicit transfer between the CPU and the device. And as I said before, they increase the performance of lower precision, despite of double precision. And at the present time, we use double precision in numerical simulation in order to have accurate results. So I would like to refer to two excellent talks that have been done during last week during the ANAMI high-level symposium in Barcelona. The first one is about Mohamed Waib from R-CCS, and he talked about the convergence and divergence between HPC and AI. And another talk given by Ryo Kota from Institute of Science in Tokyo, and comparing also scaling laws between HPC and AI. So please take a look at these two presentations because it was very interesting to compare the two worlds between HPC and AI, the convergence, the divergence, and what can be done between these two worlds. Another exercise I try to do is to compare the evolution between vector processing to MPP and CPU to GPU. So if you look on the left, the transition between vector machines and MPP machines. First of all, at the vector era, market was led by a few vendors. So namely, I cited there before, Cray, Fujitsu, NEC, for example. The cost of the solution increased a lot during this period. It was very costly to buy this kind of machines. Another fact is that HPC and scientific computing is a niche market, and it's essentially done in academic ecosystems. And the problem is that this ecosystem couldn't afford this kind of machines, so they have to find some alternative solution. So they move from vector to MPP, and essentially cluster of PC at the first time. Now, if you look at the transition between CPU and GPU, so of course there is the impact of power consumption, so the ratio between flops and WAP, and this is one of the reasons in scientific computing we adopt GPU. But HPC in scientific computing is still a niche market, and now the market is led by AI. But if you look at the market now, it's still led by few vendors, namely AMD or NVIDIA. The cost increased because it's quite hard now to acquire NVIDIA GPUs because all the market is led by AI. HPC scientific computing is a niche market still, and essentially done in academic ecosystem. And so this is also the reason why you try to use GPU efficiently in scientific computing. But we can ask a question, is AI a bubble or not? We'll see. But if costs still increase, do we have to find some alternative solution, as we did before, between the shift from vector machine to MPP machine? Now I will try to make some items concerning geopolitical context in order to see the impact on the international collaboration. So first, there are some conflicts. So I will not address all the list of conflicts we have in the world now, but mainly the two main conflicts we have at the present time is between Russia and Ukraine, but also between Israel and Palestinian people. And there is a direct impact of all these conflicts on the energy cost. This is not the only reason, but this is one of the reasons. And if you look at the graph below, you will see the cost of energy depending on time, and you will see that the tendency is to increase the increase of the price for energy. And you'll see that also there's a large increase of energy consumption in the world during the last decade. So the cost of energy is increasing. We have also some economic tensions. For example, between USA and China. This is not new, but this is still true. We have also some economic tension between Europe, China, and USA. And I take some example. One example is the last, I think, regulation given by the Biden administration about AI and the regulation that limits the export of AI technology, both from the hardware but also on the model. So they restricted the diffusion of this kind of these US technologies to some other countries. So there's for now some years regulation on technology export to some countries. And of course, the global warming and natural resource crisis, and this is not new, but this is still increasing, and there's a deep impact on the whole computing system. So on this graph, I put some tendencies about the energy consumption of the digital technology, data center, blockchain, transmission, AI, and so on and so on. And also, there is not only an impact on the energy consumption, but also on the natural resources, and essentially water, because we have to cool all these data centers, and the consumption of water to cool all these data centers is increasing also. So is the continuous increase of the use of digital technology sustainable? Does this imply some technological shifts? So we saw some technological shifts. For example, when we use GPU, we tried to increase the ratio performance per watt, or when we cool data centers or something like that, we make some shift in technology in order to decrease this impact, but the impact is still increasing. So perhaps it will have some also impacts on the usage, and not only on the technological solution in order to minimize this impact. So for all this tension we have in geopolitical, there are some consequences. Essentially, the strengthening of independency policies. So for example, different countries try to have an independency from US technology. I cite this European Processor Initiative, or for example, Fugaku, who used a homemade processor based on ARM architecture, or Chinese technology, which have been developed now for 10 years. But there are also the development of international cooperation between friendly countries and countries with common interest. And if I take the point of view of Europe, we developed for now some years international collaboration between Europe and Asia, but also with Canada, with Latin America. So these collaborations are supported by the European Commission. And we still have now for long years collaboration with US. This is not institutional collaboration, but much more rather bilateral historical collaboration between different countries in Europe and US. So now how can science navigate in this context of these technological shifts, but also crises in the world? So I think that scientific international collaboration is an essential vector for progress of science, of course, but also can contribute in the decreases of international tensions and try to help humanity to face the incoming challenges. I take two examples and make the parallel between these two examples. If you look at, on the left, you see that this is the main targets, scientific targets that have been projected for the design of Fugaku about drug discovery, personalized medicine, and so on and so on. And we did quite a similar exercise in France for the future machine, which will arrive, let's say, next year in France, which will be the second exascale machine in Europe, and try to identify scientific targets with high impact in the society. So this is not only, let's say, a picture, but I think this is a true will in order to increase the impact of science on the society and how these old technologies, knowledge, and scientific and science can help the society to face all these challenges. Sorry. So if you look at the past, it exists some large international collaboration that have demonstrated their ability to address major scientific and technical questions. So I take some few examples. And the square kilometer array, which is still arriving, or the ITER machine in order to deliver fusion energy, or an older one about the Large Hadron Collider. So all these big international collaboration help us to design some big machine, to construct this big machine, and to address some very important scientific question, but not only to understand how the universe has been created or something like that, but if you take the ITER technology system, the idea behind is to find a sustainable energy for the future. So some of the next challenges should also be addressed through large international collaboration. If you take some example in AI for science, the main interest is of sharing data sets and AI open models. As you may know, all this AI technology is based on learning, so you have to learn on large data sets and high quality data in these data sets. I take just an example. So the last Nobel Prize in chemistry in last year was discerned to three persons, and is about drug discovery and essentially in protein design, and the founder of AlphaFold and so on. But if you look at how this AI model has been designed, namely AlphaFold, is only based at the first time on the PDB, the Protein Data Bank. And the Protein Data Bank is an international collaboration between scientists who try to collect all the protein data around the world, cure the data, put in one large database, and AlphaFold can train on this large data bank. So another difficult exercise is try to make a classification grid about international collaboration. So in the world of HPC, we have to find the balance between performance and portability, for example. But in the world of international collaboration, we have to find the right balance between flexibility and support. So if you look on the left on this table, if you have some political support, so you will have funds, larger visibility of your project and your collaboration, and a short or medium-term duration. But on the opposite, oftenly the scientific domains are much more driven by political orientation than let's say, pure science. Oftenly also the partners are imposed. From the European point of view, it's clear. And there's lots of admin burden in order to set up all this collaboration and the follow of the collaboration. If you have no political support, so you have much more flexibility in terms of scientific subjects and partners, because you decide on what kind of scientific topics you want to collaborate, and you can choose also the partners you want to collaborate. And of course, there's also less admin constraint, but you have, of course, no budget or no support budget from funding agency. You can have less visibility of your collaboration, and perhaps less impact program and perennity of your collaboration. So if I take a few examples of existing collaboration, sorry about that, but I took some collaboration where CA is involved. So I will not take all the existing international collaboration in field HPCI and quantum computing. So it will take too much time. So I focus essentially on 5 of them. So first of all, the European-Japan Alliance in HPC, called the Hanami project, funded by EuroHPC. Another one is a bilateral collaboration between R-CCS and CEA on this topic. So it's about 10 years bilateral collaboration, with no specific funds for this collaboration. Another one is a bilateral collaboration between URISH and CEA. This is a virtual lab called IDAS, and it had been started in 2020, and we have a visibility up to 2028. And we have some funds coming from the two organizations, one side from URISH and the other side from CEA. Another collaboration is ADAC, so it's more of a 10 years collaboration, international collaboration between more than 15 institutions about HPC, AI, and quantum computing, and there is no fund on this collaboration. And the last one is the TPC Consortium, which is an international collaboration on AI and a large model. It's over 100 institutions, and not exactly the right number, but it's a very large collaboration between public partners and private partners. And there is no specific funds, but at the present time, there are some core projects in Europe in order to form this collaboration. So if I try to put all this collaboration in a graph, depending on the political support and the flexibility, so we can discuss about where I put the different collaboration, but clearly, for example, for the Hanami collaboration, we have large political support, but no flexibility at all. And we have larger flexibility in bilateral collaboration, for example, between R-CCS and CEA, or in the IDAS virtual lab. And I put ADAC and TPC in the middle, but it can be discussed. But the question are, what about the impact of such collaboration? And clearly, funding collaboration increase the achievement, but not necessarily the impact. So it depends on the scientific relevance of the fixed objective. So if we don't fix a relevant objective at the departure, okay, we will have some achievement because it's signed at the beginning of the contract. But what are the real impacts of science of this achievement? And also the ability to adapt the perimeter and the science and partners, exactly the same thing. If you don't choose exactly the scientific objective and you cannot choose the scientific partners, it's quite difficult to have a greater impact on the science. So now, how to improve this international collaboration? So this is some suggestion which can be discussed after that, of course. So I think that to achieve benefit international collaboration, I think we think about the role of incubators of new ideas and talents, and to be a force for proposal toward policymakers. So try to identify emerging topics where academic partners are relevant, so choose the science, choose the partner, break down barriers and avoid the village gaulois, what we call in France, village gaulois, and try to bring on young people new skills in order to renew all the ideas, strengthen the transferability and break down silos, so try to be inclusive in what kind of science we can do and new ideas. And in this idea, opening also up to human and social sciences in the project we are launching. So two examples. So I will not detail all of that because this is a quite dense slide, but some idea trying to cross, let's say, science and human and social sciences, the development of trustworthy AI for science. As you may know, there is many well-known limitations of AI, some basic problem in generative AI. So I think we can think about how to have a more trustworthy AI, especially for science application, in order to be sure that the result we can have using AI are reliable and reproducible, explainable, and so on and so on. Another emerging topics is about tensor networks. So it's very specific topics, but it could be also what I call the CPU revival. So this is in the frame of quantum-inspired algorithms. Some people who are specialists in quantum physics and quantum chemistry try to adapt their algorithms and not to use quantum computers, but classical computer in order to accelerate the calculation, the computation. So tensor network, the factorization of very large tensor into a network of smaller tensors with application in many fields, in applied mathematics, chemistry, physics, machine learning, and many other fields. So there's a big development of this kind of technology for a few years now. They propose some libraries, including all the, let's say, the numerical kernels that can be used in the classical numerical scientific computing. And it has been applied in many different fields. And we have a first application of this technology in CA, application to nuclear fuel modeling. So it's quite far from the initial quantum chemistry. And so I will not detail all the problem, but essentially what we have to take off this slide is when you use the tensor train, you minimize the memory footprint. So for example, if you look at classical methods, the memory footprint is a power of d, n power of d, where n is a number of mesh elements. And when you use a tensor train or tensor networks solver, the memory footprint is an order of magnitude less, since it's about log n. And exactly the same time for the CPU. So if you like on the graph on the right, depending on the number of meshing elements, you see that you have, let's say, the flat curve of computing time. So it's quite independent of the size of the mesh. And if you use classical method, you have, of course, an exponential CPU time. So it could be also interesting to look at this kind of new emerging technology, and especially this is some new numerical methods coming from the quantum theory, and apply to classical PDE solvers or classical system we have to deal with in a classical HPC simulation. So it can be also, there are some thoughts about using this for solving Navier-Stokes equation and so on and so on. So now to conclude, so I didn't use this tool. I will try it another time. Free AI conclusion generator. I think it could be interesting. So I don't use it for my conclusion, but what can we do for science? So clearly now we have to use, and it's already used, artificial intelligence in science. So what is the place of science and fundamental research in this large ecosystem between HPC, quantum, AI? And clearly the HPC world or the simulation, numerical simulation world will still a niche market. But HPC is a unique place where we can embed computer science, high-end technology, fundamental research, and we have to find the right place and the right balance between all these ingredients in order to continue to make some progress in science. So the important thing is to find our key message, define a common goal, what is the common denominator between HPC, AI, and so on. So without application, it's useless. So we still have to define the application and the target we want to solve in order to make some progress. Another thing which is very fundamental is that all we do and what we will do is still linked with data and observational data, experimental data. So the data is now a key point in all this HPC ecosystem. Okay, we have to use AI for science, it's clear, but we have to think about not to use brute force and to think about specific models to answer to specific questions. And also to, as I mentioned before, to have a look at what we call trustworthy AI and to identify what are the bias, what are the validation of the results produced by this kind of technology. So I think that international collaboration could help. So it won't be a miracle solution to solve all the problems in the world, but it could contribute. So I think the international collaboration, there is a role of an incubator of new ideas and talents to be a force for proposal towards policy makers. So try to identify the good or the right question to answer, to find the right partners in order to collaborate with them. So identify the right ideas, right people, put a little money, of course, at the beginning if you want to make some progress. And after that, let's be convincing about funding agencies in order to increase the collaboration on specific targets we have already chosen. So perhaps we will have a new HPC cake. So thank you very much. And if you have any question, it will be a pleasure for me to answer.